Yeah, thank you for the invitation. Yes, I'm talking about neural parameter calibration, and to kick it off, I'm going to start with an example that isn't learning pictures of faces. This is the global barley trade in 2021. This is data from the UN, and basically you can see the flow of barley between importing and exporting countries. The blue nodes are the exporters, or the export quantities. The red nodes are the import quantities in metric tons. And these sort of supply chains, global trade flows are incredibly complex networks of supply and demand flow. They are very dynamic. They change rapidly all the time. And they can change without the change being reflected in global costs, prices, these sorts of things. So what we want in this case study is to kind of learn an underlying economic utility matrix that can help us understand the dynamics. We basically want to understand, why does it look like this and why does it change the way? And the way what data looks like is, this is the UN data we have for each pair of countries. We have flow of the commodity, in this case barley, any commodity you want, between countries, and we actually have two reported values. So we have the value reported by the exporting country, and we have the value reported by the importing country. So in this case, this is the exports of Australian barley to China. China reports a value, and Australia reports a value to the UN. And they don't match in a lot of cases. This is typical for all commodities, all countries. And there's all sorts of reasons why they don't match. The main reason is just discrepancies in reporting standards. So for example, something that's very typical is that some countries report all imports, regardless of whether the part of the import is then exported to a third country. Some countries only report the imports that are consumed domestically. So there are just differences in standards. There are also political reasons. Sometimes commodities are embargoed and countries don't want to report accurate values to the UN because they're not supposed to be importing or exporting more than a certain quantity. And they're under no legal obligation to report any of this data. So there are just discrepancies in them. So discrepancies in the figures. So there's an uncertainty. What I'm trying to say is there's uncertainty, but the uncertainty is epistemic. It's not random noise. It's not aleatoric. And then we also have missing values. So a lot of the values sometimes are missing, and the missing values can mean no trade, or it can mean no reported value. So we have this very noisy, gappy data set, and we want to fit a model to it. And the model we want to fit to it is actually, it's not that important what the model is specifically. It's an optimal transport model. But basically what it looks like is we want to understand this total volume flow as a function of time. And we want to model it using some kind of utility matrix. So the C is a utility matrix, a cost matrix that kind of models the costs, but in an abstract way. So when I talk about costs, I'm not talking about transport costs. I'm talking about more of a utility, trade barriers. It's an abstract kind of measure of how useful or efficient it is to transport a certain quantity of material from one country to another. And then we have these marginal constraints that are basically just modeling supply and demand. So we have this setup of comprising a model equation, observations, which in our case are the data from the UN. Those are the transport flow and the marginals. And then we have our model parameters, those are the things I've indicated in green that we want to learn. In this case, specifically, we just want to learn the utility matrix, the entropy regularization term we just fix. And the idea behind neural parameter calibration, which is the framework that I'm proposing, is to take the data, so the transport plan, and to train a neural network to output an estimated cost matrix, but not in a way where we just have pairs of transport plans and cost matrices, and it's a deep learning approach which can match the observations with the prediction. But we want to kind of fit the actual model to the data. We want to make use of the fact that we have an underlying model and incorporate the model into the training procedure. So in this case, in the case of the global trade, we want to have a neural network that gives us cost matrices as a function of time, of course, but also the transport plan. So the general kind of setup that I'm considering in this talk is one where we have model equations, model observations, and model parameters, okay? And the model equations broadly are anything that is a dynamical equation. It could be an ODE, a PDE, SC. It could just be a set of constraints, like in this case study that I'm showing. The dynamics can be very complicated. You can have things like the emergence of self-organization, complex nonlinear physics. And then you have observations, data sets that in real life are usually very noisy, they're very gappy, they are a bit of a pain to work with sometimes. And then we want to fit model parameters to the data set. And the model parameters can be non-unique, meaning we have several different parameters that will all reproduce the data that we see. The model parameters that I'm considering here are usually very high dimensional. You're learning adjacency matrices with hundreds of thousands, millions of edge weights. And possibly, and actually this is always the case, you have data model mismatch because you're trying to fit some kind of physical model to a real life observation. So this optimal transport plan model that I'm proposing, I'm not saying this is the actual driver. What I'm saying is we want to fit this model to the data because we think it will show us something interesting about the underlying dynamics. So we have this sort of data model mismatch, and we want to quantify the gap between the model and the data. And so all of these problems, if you look at these problems, would kind of call for different approaches. If you just want to fit the parameters, there are obviously tons of optimization procedures that you can use, but they're not going to give you a distribution of the parameters. They're just going to give you an optimal guess. So if you want more of a distribution over the parameters, you might use something like a sampling scheme, Monte Carlo scheme, but they can struggle in high dimensions. So even trying to learn 10, 20, 100 dimensional distributions with the sampling scheme can usually go awry. Then if you want to learn a functional relationship between data and model, there are Gaussian processes, but these are difficult to constrain with physical model. So the framework that I'm proposing using neural networks kind of addresses all of these challenges and kind of manages to solve a lot of the problems that you would have with any of those individual methods that I showed. So the idea, the training procedure is as follows. We take our observation, the observed data, and we input it to a neural network and have the neural network output the parameters of the equation. So the adjacency matrix, the model parameters, the diffusion coefficient, whatever you want to learn. And then you take those parameters and then you input them into your model equations, whatever they are, PDE, ODE, SD, and you solve the equations using the parameters, using a solver, a Runge-Kutta scheme, whatever it is. And that will obviously give you a prediction, like a predicted time series, a predicted snapshot of the system. And by comparing the two of them, you get a loss function, and then you use this loss function to train the neural network. So how do you use, what does the loss function look like? Well, training the neural network requires differentiating through this entire cycle, okay? Which includes differentiating through the model equations. So if we look at the cycle again, just in a kind of linear way, we go from neural network output to parameters to model equations to the prediction to the loss. And if what we can do is we can track these gradients at each step and then concatenate them using chain rule to get the gradient of the loss with respect to theta. So these are the neural network parameters. We're using the term parameters to talk about both the neural network parameters and the equation parameters. Sorry, it's a bit confusing. So theta are the weights and biases of the neural network, and lambda are the parameters of the equations that we're trying to learn. And so we can kind of concatenate these. Using the chain rule, we combine these different gradients to get the gradient of the loss with respect to the neural network. Now, this step is this is easy. You can always get this from any kind of autograd package. This is also typically easy. The tricky part is getting the gradient of the predicted time series data or the predicted data with respect to the model parameters. And so this whole procedure, one of the limitations is that the model equations have to be differentiable with respect to lambda. I've never encountered a situation where you can calculate this using an autograd. So most of the packages that are out there that are used for machine learning will allow you to differentiate through a solver, Runge Kutta or ODE int or something, whatever you're using. And we had to talk about JAX, so I think the packages that are being developed, they allow for auto differentiation through the equations. So just going back to the optimal transport problem and applying this scheme, what we're doing is we're taking the transport plan, we're putting it into the neural network, having the neural network output our cost utility matrix. Then we solve the model equations using this iterative, what's called proportionate fitting procedure, or Sinkhorn or RIS. It has different names, but it's like a and this will output a prediction T, and we can this should be T hat, sorry, and we can compare the two, calculate J, and train our neural network. And so the neural network is a function that maps cost matrix, that maps transport plans to cost matrices. So just to show you some results, here what I'm showing, the green line is the predicted utility, again on the Australia-China barley trade example. The blue line is the unit cost. So this is kind of the market price adjusted for inflation. And you can see that the utility that we're learning has a lot more structure than just the market price, which is fairly constant if you adjust it for inflation. And you can see that there's a lot of structure. You have peaks here where you have periods of low yield in Australia. You have a general downward trend post 2001. China joined the WTO in 2001. And then in 2018, the US-China trade war erupted, and this had huge implications for not just US-China, but also Australia-China trade. China imposed a 80% import tariff on Australian barley in 2020, which has since been revoked. And you can see that this had a huge impact on kind of the utility, and as a consequence, the flow went back almost to zero in those years. And so here what I'm showing is, again, the data, obviously the reported values from the exporters and the importers. The blue dotted line is the prediction that you get from the predicted utility. So by taking the cost matrix that you learned, putting it into your model equations, and getting and calculating a prediction. And the uncertainty, in this case, I'm going to come back to that, comes from obviously the uncertainty on the training data. So once we have a trained neural network, we can just push, in this case, we can sample different transport plans by just picking different reported values for each year, for each edge, pushing them through the neural network, and that will give us an uncertainty on the predicted utility. And then we can take that uncertainty and push it forward onto the transport plan. So the uncertainty on the predictions basically comes just from pushing the uncertainty on the data through the trained neural network. But I'll come back to that in a second, and you can see that the uncertainty in this case matches the uncertainty on the data very well. One other example that I wanted to show, just because the results are interesting, I think, is global wheat trade. This is the change in trade volumes from 2001 to 2002 as a consequence of the war in Ukraine. So Russia and Ukraine are major wheat producing and exporting countries. Russia is the world's largest exporter, and I think Ukraine is fifth largest. And obviously the war had huge consequences. It was incredibly disruptive to global wheat trade because the exporting routes through the Black Sea were basically cut. And so what I'm showing in this column is the change in trade. Export volumes from Ukraine, that's the top row, and Russia, that's the bottom row, to different countries. And you can see that kind of trade to all parts of the world basically collapsed as a consequence of the war. So you can see the trade to North America, Africa, Asia, South America, they imploded. And this implosion was roughly uniform. What I'm showing on the right is the change in trade utility. And here the distribution is very much skewed towards the global south. So what you can see here is that even though trade to, let's say, for example, Canada dropped by, I think, 75%, which are values that are similar to, for example, Namibia, Kenya, the difference in trade utility to China was to Canada, sorry, was basically zero. So that there was no change in the trade and the ease of doing business between Ukraine and Canada. Whereas if you look at, for example, the effect on African continent and also Iran, Southeast Asia, the drop in utility is disproportionate. So the change in trade barriers disproportionately affected the global south. And this is a kind of structure that you don't see just by looking at the change in trade flows or by the fluctuations in market prices. Okay, but this is just an example. Now, I want to go back to the uncertainty quantification. So in the example I just showed, we basically pushed the uncertainty on the training data through the neural network. But of course, there's another source of uncertainty, which is that you may have different parameters that all fit data. And you kind of want the distribution on your parameters. So in this example I'm going to show, we're going to look at epidemiological modeling. And just to start this, looking at a very simple SIR model, it's a compartmental model of epidemics. You have 3 compartments, susceptible agents, infected agents, and recovered agents, and you kind of want to, and you have a Stratonovich SDE that kind of models the transition between the compartments. And what we want is we want to learn these 2 model parameters. So let's just say a 2-dimensional problem. We have an infection parameter and we have a recovery parameter. And this is what we would observe, time series of the 3 compartments. At time 0, everyone is susceptible to the disease. Then you have an outbreak and the sort of peak. And then eventually everyone has recovered and the infection dies out. And we want to fit these parameters to this data set. And this data set was generated from an ABM simulation. So it's not generated by running these. So let me go. Yeah, so it's a noisy data set, and we can obviously calculate the ground truth distribution on the 2 parameters just by doing a grid search. You can see that we have this sort of banana-shaped distribution. There are lots of combinations of parameters that would fit the data roughly equally well, and we would like to have an overview over how many. We would like to know the marginal distributions, joint distribution of the marginals of the parameters. So if we start the neural network and we initialize it at some random point, it trains. It learns to find a set of parameters that will reproduce data. It will obviously eventually meander into this region of high probability and it will stay there. This gives us an optimal value. But of course, we have this training process as well, and it's traversing the parameter space and it's calculating a loss at each parameter that it hits. And we can kind of leverage this process to get an estimate of the distributions on the parameters by training multiple neural networks in parallel, which we can do. It's efficient because these individual chains don't depend on one another. We can kind of initialize the neural network from several different points in the parameter space and train it. And the more of the chains we run, the better our approximation of the joint distribution will be. So here we're training 256 neural networks in parallel, and obviously these chains put together will give us an excellent approximation of the joint distribution. And the reason it works so well is because they're all purely gradient driven. They each find the region of high probability quite quickly. So you spend very little time meandering around low probability regions. You don't need a burn-in. You don't need to chop any of these samples as you would typically do with an MCMC scheme, for example, because these samples are they are accurate. I mean, they are the loss at this point, and sampling the same point multiple times doesn't give you any extra information. It doesn't, and it also doesn't skew the distribution. So this is fairly fast and efficient way of calculating the densities on the parameters, and so we get this is the ground truth, and these are the estimated marginals on the parameters. So the blue line is the neural estimate. The pink line is an MCMC estimate using a Langevin scheme, Metropolis adjusted Langevin algorithm. And the dotted line is the ground truth, and the neural network then finds the marginal distribution on the parameters pretty much exactly, orders of magnitude better than an MCMC scheme. And it's also significantly faster to run because you don't have a burn-in and you have much faster convergence, or much faster convergence to this sort of region of high density. So getting these marginals for the neural network takes about 4 minutes on a CPU, and our MCMC scheme took about 30 minutes to converge. And then one of the application studies that we did was to a real data set of spread of COVID in Berlin. This is work with Greg and also Christoph Schütte and Tim Conrad in Berlin. And what we have is data of spread of COVID-19 in Berlin. We looked at March to October. The data that we have are number of infection counts, symptomatic cases, people who are hospitalized, and people who are in critical conditions, of ICU patients. And same principle as before, we have this data set, and now we have a compartmental model that is a little bit more complex than the SIR model that I just showed, but it's the same principle. You have susceptible agents, infected, symptomatic, hospitalized, people in critical condition, deceased, people who've recovered, but then you also have like a quarantine. So this is a contact tracing mechanism. You have quarantine compartments and exposed people who've been exposed to the virus. But you know, same concept, and the parameters that we want to learn are these transition rates between these compartments. So in this case, we have a 15-dimensional parameter space. Same thing as before. We train the neural network. We get distributions on these parameters. So the blue distributions are the neural estimates. The pink ones are estimates using an MCMC. And then we take those estimates. We can sample from the distribution, put them back into the model equations, and produce an estimate of the data that we see, as well as a projection into the future. So the period, so we took the data set and we kind of split it into a training and a test part, or a calibration and a projection part. The section from February to September we used to calibrate the model, and then we made a projection 2 months into the future to see how well it would predict the actual trajectory of the pandemic. I'm just showing the results on critical compartment here, but we saw a calibration accuracy improvement of 50 to 300%, 50% on the calibration section. So that's this section here. This plot is the corresponding MCMC calibration, and then it was orders of magnitude 300% more accurate on the prediction, while running about 6 times faster. So it takes about 10 minutes to calibrate. Again, on a CPU, you can run it on a GPU, and it's even faster, while the MCMC took about 45 minutes to converge. Okay, one last case study that I wanted to show. This is, again, work with Greg and Mark Girolami. Cambridge is looking at network adjacency matrices. So this is a project that we did where we learned graph network adjacency matrices from data. And one of the applications that we looked at was power grid dynamics. So power grids, you can model power grids using the Kuramoto model of synchronized oscillation, where you have nodes in the network and they're coupled through the network edges. They're oscillating with a certain phase, and because they're coupled, the phases will synchronize over time. And the synchronization process follows a second-order differential equation, which is Kuramoto model. And there are a bunch of parameters. The parameter that we want to learn from observations of the network dynamics are the AIJs, the edge weights. So this is the network adjacency matrix. And the data that we have is data from the British power grid, the transmission grid, about 700 nodes, I think. So yeah, so it has about, so the network adjacency matrix is on the order of about 500,000 edge weights that you want to learn. And then there are a couple of other coupling constants, inertia, friction coupling constants. There's also some noise, some Gaussian noise on the data. And power grids, they synchronize over time if this equilibrium condition is met. The PIs are the amount of power generated or taken out of the network at each point. So at each point, power is either consumed or generated, and the equilibrium condition is that the amount of power put into the network has to equal the amount of power taken out. That's basically it. And the data, so the data that we have are observations of a line failure. So if the network is synchronized and then there's some sort of disruption, like a line failure, this causes a cascading perturbation to sort of ripple through the network. So the network in equilibrium is oscillating in unison, and then if a line is cut, there's a perturbation, and this ripples through the network. This is what I'm showing here. So at time t equals 0, we simulate a line failure. So we just cut two edges here in the northwest of England, and this causes a disturbance to ripple through the network. You can measure the disturbance at each point in the network. And so the phases, what I'm showing on the y-axis, the phases they're disturbed, and then eventually they reach a state of equilibrium again. And from observing this disturbance, you can infer, or we managed to infer the network adjacency matrix, and therefore, by extension, the location of the line failure. So from observing just how the network responds at different locations, you can sort of reconstruct where the line failure, where the disturbance originated from. And the way we train the neural network is much as before. We have a loss function that contains different components. First of all, the data model mismatch. So this is the mismatch between the predicted time series and the time series that we observe. Then we penalize the trace, so that the diagonal of the adjacency matrix can't be learned because these terms here going to be 0, so you manually set the trace to 0. It's an undirected graph, so we enforce symmetry by adding this constraint to the loss function. And then we purposefully sort of underdetermine the problem by only looking at a snapshot of the disturbance in the first 3 to 4 simulated seconds. And so you have n time series, but you're trying to learn an order n squared adjacency matrix. So it's an undetermined problem. But an additional constraint that we put on the loss function was to say that the adjacency matrix that you should learn should be very close to the unperturbed, so the power grid without the line failure. So you should be learning an adjacency matrix that's very similar to the power grid without a line failure, but is maybe different in a handful of locations. And what we do is we train the neural network, and we find, and then we can plot the densities on each of the edges. Densities meaning the predicted edge weight, or rather a distribution over the predicted edge weight. And if we then sort all the edge weight predictions by the error between the complete power grid and the inferred power grid, the two edges that have a predicted weight of 0 are exactly the two edges that we cut. So we've labeled them with these edge indices. So the prediction on, so there's a prediction on these two edges that has a mode at 0. It also has like a little secondary peak at the original uncut value, and then all the other edges are basically predicted to be very close to the edge weight, but they are without the line failure. Interestingly, all the candidate locations for the line failure are kind of in the vicinity of the line cut, so they're all sort of here. So the neural network manages to not only find the edges that were cut, but it also kind of detects broadly where sort of it manages to sort of zone in on the region of the line failure. And having a distribution on these on the edges is incredibly useful, because in general there's going to be several candidate locations, and you want to be able to perform some kind of hypothesis testing. So you want to be able to calculate the p-value, and you want to be able to gauge how likely it is that a line failure occurred in a certain location. So having a distribution is incredibly useful. Much more useful than just having a single optimized guess. And again, calculating this took about half an hour on the CPU. I think in the interest of time, I'll skip over that. We compared the performance of the adjacency matrix estimation to other schemes, including OLS scheme. basically what we found is that the neural scheme, if the noise on the training data is very low, regression is typically a more accurate method if you just want a guess on the adjacency matrix. You don't want a distribution, you just want an optimized kind of guess. But as soon as you add just a little bit of noise to the training data, the regression performance decreases significantly, whereas the neural estimate is much more robust under noise, while also running about an order of magnitude faster than regression scheme. And yeah, I think I'll stop here. Thank you for listening.
Are there any questions?